Hi, Maciej.
Good afternoon.
So people is joining already, so I guess we can start. So good morning, everyone, and thank you for joining for this webinar entitled Data-Driven Approaches to Smartly Engineer Porous Materials. If you joined previous webinars from India Materials, the dynamic is going to be more or less the same. The presentation is going to last for around 45 minutes, and then there will be there will be time for questions and answers. So either you can type them down in the chat or in the questions section, or you can use the raise my hand functionality, and I will activate your microphone in the end so that you can intervene and ask Maciej your question. Nevertheless, I will read also the ones that you type down in the chat. So without further ado, I have the pleasure today to introduce our speaker, Dr. Maciej Haranczyk, senior researcher at India Materials Institute. Maciej received his PhD in chemistry from the University of Gdańsk in Poland in 2008. And during his graduate studies, he received numerous research fellowships to collaborate with researchers at Pacific Northwest National Laboratory, the University of Southern California, the University of Sheffield, and others. Then after graduate school, he moved to Lawrence Berkeley National Laboratory, which had offered him a prestigious Glenn Theodore Seaberg postdoctoral fellowship. And then he was hired into tenured scientist position in 2010 and promoted to a staff scientist position in 2014. The following year, 2015, he joined the India Materials Institute as senior researcher in order to establish a new research line focused on information-driven materials discovery. And he's going to talk today about the most recent advances his group has done in this area. So, Maciej, the floor is yours.
Thank you for introduction. Good afternoon, everyone. Thank you for joining us. Let me share my screen. Okay.
Yeah,
can you see it? Okay, thank you. So today I'd like to give you an overview of research activities in my group, and my group is interested in discovery of materials. Just to be more specific, we are working with very different applications and different materials that fit in the family of nanoporous materials, but we are not so much tied into one application. We are really interested in how we can use computers to discover new materials and do it faster and cheaper. So as you probably know, these days, an average time from the idea of new material to enter the market takes about 20 years, and we would like to shorten this time. So today I will give you an overview of our approach, and I will show you a couple of examples. Those will be examples which are really the work of PhD students and postdoc working with me: Julia Lodico, Junchen Zhao Li, Aditi Krishna Priyan, and Corey Simon. So let me start. So porous materials. So porous materials have some internal surfaces and internal voids, and usually as a chemist we are interested in how some targeted substance interact with this internal surface. So those interactions can be of interest in various applications. For example, in a gas or liquid storage, and in those cases we will have a gas molecule like hydrogen or methane and would like to adsorb it on the internal surfaces. And one of the predictors of performance of material in this case will be adsorption at particular condition or working capacity. So basically how much of this gas we can store between adsorption and desorption stage. Another application of those materials is separation. In those cases, we have a mixture. Our targeted substance is a mixture, and we want to use selective adsorption, basically to separate two different molecules or more molecules. And here examples are, for example, CO2 capture, noble gas separations, or hydrocarbon separations. Another application of nanoporous materials, especially ones that have some active sites on internal surfaces in catalysis. In those cases, the targeted substance or molecule of interest will adsorb and then will undergo a chemical reaction. And here example application could be hydrocarbon cracking or decomposition of dyes or toxins on internal surfaces. So to be more specific about materials, we are interested in different families of nanoporous materials: zeolites, nanoporous clays, metal-organic frameworks, porous molecular materials. On this plot, those families are ordered basically by long-range order and the strength between building blocks. So zeolites are basically the building blocks are strongly bound and they are crystalline. On the opposite, we have porous molecular glasses, which are amorphous and soft. Those materials share similar design challenge. So in particular, to give an example, metal-organic frameworks, those materials are made by organic linkers, metal or metal oxide clusters, to form the three-dimensional periodic frameworks that are porous. A number of synthesized MOFs is around 10,000. And we can also predict new materials by changing building blocks. And we have databases of those materials reaching hundreds of thousands. And the challenge is, out of so many different materials, which one was particularly good for specific application? And the challenge is how we find those best materials. And similar in other types of materials like natural clays. In those cases, the structure is fairly simple, a crystalline structure, but we can change macroscopic properties. We can change also chemical properties by ion exchange. We can change properties by different physical treatment. And here in this plot, we show basically a set of nanoporous clays that were heat treated with different temperatures. And you can see in this plot the number. We can basically tune surface area depending on how we treated the material. And here the design challenge is similar. Out of all possible processing techniques, how do we choose the right combination of techniques that give us the material with right properties? And we have this enormous search space through this experimental parameter space. So let's think about how do we design a material for specific applications. So in traditional R&D process, we usually have some initial criteria. So we focus on families of materials, we focus on applications, so we have some performance measures, and we have some initial data, either from literature or initial experiments. And based on this initial information, we make a prediction that there is a better prototype material that needs to be synthesized and tested. And after we test it, we will know if it's better or not. And if the material fulfills criteria, which is rarely the case in the initial stages, we have a candidate to commercialize it. If the candidate material doesn't fulfill criteria, we have to basically what we learn include in our decision making and start another cycle of material optimization. So because normally development of a material to fulfill all the design criteria is very long, we need a lot of cycles. The whole process is very time consuming and very costly. So we'd like to accelerate this part. And there are a number of ways that we can do it. So, for example, robotic experimentation is one way. We can do high throughput experiments and basically collect more data, try to find this material faster. If we do simulation work, we can use basically bigger computers and do more predictions. In both cases, it is still expensive. So the idea in my group is basically replace this expensive part of R&D process with machine learning. So basically what we want to do is to create a digital twin of the real experiments that will allow us to synthesize and predict properties of materials before they are made, and do it fast enough so we can explore various candidates and identify best solutions at minimal costs. So here we basically try to build a function that correlates the structure, our prototype, with property. And in order to do it, we need, with machine learning, we need a couple of components. So first, we have to think how we represent our structure. So in a classical approach to machine learning and property prediction, we think about representing structure with a set of descriptors. So if we talk about materials that have crystalline form, those will be some properties of a crystal. If we think about materials that were synthesized in the lab, our descriptor of a material can be basically a set of parameters that correspond to synthesis conditions. And then we'll correlate those descriptors with properties. So we need some initial test set on which we'll fit this function, and some mathematical framework that will allow us to fit this function and correlate structure with property. So let me go into a few more details about those required components. So when you think about initial data on which we can train, we can use simulated data. So for example, in case of crystalline porous materials, we can build or predict crystalline structures of MOFs or zeolites, basically by assembling those building blocks in different ways. And currently there are a number of databases through my work and my work of my colleagues available. And there are hundreds of thousands of materials. There are also materials that we synthesize and they are deposited in a Cambridge structure database. Those structures typically contain solvent and other experimentally relevant information that we need to remove in order to run simulation. But there is also a curated set called computation-ready experimental MOFs, core MOFs. So if you are interested in running those simulations, basically the data set of structures are available. So once we have databases of structures, we can predict adsorption properties for various species, hydrogen, CO2, methane, and so on. And typically we use a grand canonical Monte Carlo scheme. In this case, we study basically equilibrium between gas phase and adsorb phase. We have to include certain assumptions in those simulations. So for example, we describe interactions with Lennard-Jones potentials. We assume we take Coulomb interactions either from electronic structure methods or from some machine learning techniques. And we have some additional assumptions such as we treat structures rigid and so on. So these days, those simulations are fairly straightforward and we can run hundreds of thousands of them using a small cluster computer. So we can generate large data sets for which we can train or build machine learning models. One comment that's important is when we want to build a machine learning model, so the idea of machine learning is basically learning from examples. So if we are interested in predicting materials with high performance, we need to ensure that our training set have enough of those examples for the machine learning technique to learn. And this is especially important when we work with experimental data sets. So experimentalists tend to record successful experiments. But for us doing machine learning, the failed experiments are equally important. So if you're doing experimental work, it's worth taking track of failed experiments. All the materials that have poor performance or we're not able to synthesize, just keep track of it, because this is extremely valuable for machine learning approaches. So once we have data sets, it's important to choose a machine learning method. So in my group, we have lots of success with decision trees and this family of frameworks. So in decision tree, we basically build this kind of decision tree that can approximate a function based on values of the argument, and we can do it in multiple dimensions. And what was observed is that this quite simple method, it works better if we have if we can build an assemble of those decision trees. And here comes the family of methods of the random forest, decision forest, extra tree regressors. And in those methods, basically we build a large ensemble of decision trees, and depending on implementation, those decision trees were either built in a different way. We split the branches, or they are trained in different subsets of the data set that we have. And typically, once we build a model, we assess the performance visually. So we can plot, for example, the plot of real experimental data or simulated data versus predicted. And if our predictions are on diagonal, then our model works very well. The more spread we have, the model is working less accurately. We can also use a number of metrics to estimate quality of the model. Coefficient of determination R square, for example, is commonly used, so we can look at mean and absolute errors. So what is the advantage of using decision trees? It's basically has a proven track record to the medium-sized problems in chemistry, like the ones that I will be presenting today. The disadvantage of this method is that we have to spend some time developing new features or new descriptors that are appropriate for the problem. I want to mention it, especially in the context of what is going on. There are other techniques available. I will here show you the highlight of work of my two former students of mine, Liqiang Lin. So, for example, it's also possible to use neural networks, convolutional neural networks that can learn features or descriptors from data. But the disadvantage of those methods is that typically they require very large data sets, which we don't have in material science. So in some cases of predicted material structures, those data sets are large enough to actually use those techniques, but this is quite rare. And then on the other side, there are Bayesian optimization types of techniques, which can operate with very little data, and they are very appropriate to when we work with experimental techniques, and we want to basically identify best materials with least number of experiments. So this is a framework that can be used, and I recommend you look to this publication by my former student Corey Simon. So in my group, we think that the random forests basically are the good middle of the way technique, appropriate in both to both work that involves simulated data and experimental data. So another important part in this framework are the descriptors. So if we have lots of different structures, like let's say meta-organic frameworks that have different morphology, different chemistry, the question is, how can we represent? What are the important features for those? And through my years of experience, basically, those are my summary of my work. It's basically that we have to think about scale at which a material operates. So what is important feature of material that gives certain property? And I will illustrate it with an example soon. And also it's important from the practical point of view that some of those descriptors can be interpreted by humans, by other researchers. And the reason for that is that if we discover new material, and as a computationalist, I go to my experimental friend and say, can you make it? The obvious question is, why should I make it? And then having meaningful descriptors which help us explain why our predictions are valid, why it's worth to try, is very, very useful. So let me illustrate, for example, what it means to have the right scale of descriptor. So we're talking about adsorption applications. So the main property we are interested in is adsorption isotherm. And here is an example adsorption isotherm that basically tells how much of the gas can be adsorbed at various pressures. And if we think about adsorption at the low pressure, is basically a Henry regime. So we'll be talking about basically a slope of an isotherm in infinite dilution. And if you look at how its Henry coefficient is calculated in simulation, we see that there is this sampling of this exponent term that includes a negative insertion energy, which is basically a interaction energy between the gas molecule and a material. And if we do this insertion sampling for entire structure, we get this energy histogram, like the one here. And what is interesting, if a structure has a strong binding sites, so if there are certain features in the structure that strongly adsorbs, those features will correspond to very negative, so strongly attractive energies, and they will dominate Henry coefficient. So in other words, if we want to predict a structure or adsorption of a molecule in a structure at low pressure, we have to focus on the local features that can be potential binding sites. And we can do it, for example, we propose a technique called Voronoi energy, and this is the technique that allows us to use Voronoi technique to decompose the material structure and get this Voronoi graph representation, which the blue nodes, as indicated in this picture, will show basically a centers of empty space. And if we calculate energy or interaction energy of a gas molecule in those places, and we choose the one with lowest energy, that will be a good indicator if a material has a strong binding site. So we can predict it, have this Voronoi energy descriptor that captures the adsorption low pressure. And it's similar if we move to high pressure regime. So if you look at high pressure regime, we will have so much of gas molecules that they will be occupying entire void space of a material. In this case, we need a global descriptor that captures information about how much of the empty space or a free surface for the molecules to be adsorbed is in the material. And this, in fact, was there was this empirical rule called Chain rule that basically said that you can adsorb 1 weight% of hydrogen at every 500 square meters per gram of material surface. And you see this correlation is quite strong. But then we came up with another observation that if you use empty volume as a descriptor, you can get even better model. So in this case, the correlation is linear, so we don't need any sophisticated machine learning. We can just use this linear model to predict adsorption at high pressure. So I hope that those two examples shows that the selection of descriptors is very relevant to the application. So over the years, probably more than 10 years, my group has explored different descriptors. So we have right now the whole database of different descriptors. We have structure and porosity descriptors that I will show in another slide how they're calculated, but basically those are the descriptors that have they are easy to interpret, and we can choose the right ones for specific applications. We have also topology-based descriptors, which are multi-scale in a sense that they can capture features like cycles that are present in a structure, or voids at different scales, so both small and large in one descriptors. We also take advantage of other work in the literature. So there are other descriptors called word embeddings that can capture information about chemistry in of a material. And then another example of a descriptor is, for example, this energy histogram that I showed before. So this is basically a histogram of interaction energy between gas molecule and a material, and we can use this plot basically as a feature vector and use it in machine learning. So just to illustrate it, for example, to calculate descriptors related with porosity, we need to develop the whole framework. So fortunately, this is already a couple of years old, but this basically illustrates, in order, if you want to calculate, let's say, the largest size of the largest pore, or the diameter of the largest spherical probe that can travel through material, we need to develop software that will do it. So in our case, we developed this code called Zio++, which can start from the structure of a material. So we basically have a crystalline unit cell, and then we employ Voronoi decomposition technique that for sets of particles give us this tessellation, which edges of the Voronoi cells are equal distance of to the corresponding atoms. And by analyzing this Voronoi graph, we can, for example, find different paths for different probes, and in particular find what is the largest sphere that can diffuse through material. We can identify accessible, inaccessible regions and calculate corresponding surfaces and so on. In case of topology-based descriptors, here is a good illustration. So when we have a set of particles, our atoms, we can assign to them a function like the size of an atom, and we can keep increasing the volume of this function, so radii of this function, and see what are the topology features that are present in the data set. So here, for example, you see in this plotted particles the volume of increased radii, we have this red cycle formed, and as we keep increasing radii, we will have another cycle, the blue one, formed. And at some point, if we keep increasing the radii, basically atoms will occupy the empty space within this cycle, and the cycle will disappear. So by going through the whole range of this radius that we can assign to this atom, we can monitor when those features appear and disappear, and we get this persistent diagram that later can be converted into persistent image, which is basically its version that allows us to compare those persistent images for different materials in a uniform way. Okay, so here are some examples of applications, and I show here 3 applications that from left to right go from our earliest model from those are 2014, 2015 to the newest work. So on the left is the first model that we have for prediction of looking for materials for noble gas separation, xenon krypton, which is important for medical applications, space travel. And it's quite expensive, it's quite expensive. So we try to find a material that can separate it in an adsorption process. So here we show a model that predicts selectivity, xenon krypton selectivity for various meta-organic frameworks. And I think what is important is you notice that it's quite a spread. For those models, it's not very accurate, but if you look at the highest performance, so the upper right corner, you see those predictions of model is good enough to identify the best structures. And indeed, with the best material we found, SBMOF1, we're able to synthesize and test, and indeed this is the highest performing material for noble gas separation. In the middle column those are models for xenon adsorption, and the lower plots are for propane. And as you can see, those are models that were developed in last year, and you can see that the points are much closer to diagonal. That means that you see basically the evolution of our descriptors. With better descriptors, now we can build much better models, and this is further illustrated on the right, in the plot on the right, where we compare models for CO2 adsorption at different pressures, and we just look at the R score for those models, and we try different families of descriptors. So the green line are the basic chemistry descriptors. We have also topological and a structural and porosity descriptor, and as you can see that models that combine more descriptors, so the better, the more information we have about the structures allows us to build much better models. I think the conclusion is that for those simple kind of adsorption and separation, we can build models for those families of materials pretty well with all the descriptors that we have. So I consider it a done part of my work. So right now I'd like to highlight you another application that is related with experimental data. So this is switching, and I will show you some results that we obtained in collaboration with Tulsa company. So Tulsa is a mining company that basically excavates clay materials. And we are in this project, we are thinking how we can use those clay materials, or how we can convert those raw clay materials into higher volume materials. In particular, we're looking for nanocatalysts for acid-base decomposition of organic dyes, and we use a chlorophyll example. So as a reminder, so as a reminder, we have a nanoporous clay can have different structures. They can be laminar in shape, like Montmorillonite, or they can be fibrous. And then I mentioned earlier, we can, when we excavate the material out of the ground, we can process it into higher volume materials using different processes, mechanical, chemical, and physical treatment. And here is on the right side, I just show a example of such industrial processes to convert raw material into clay product. So the question is, how do we convert, what kind of processes we choose to convert raw clay into good nano catalysts. So in this project, we are given some of historical data sets that were available in the company. We had 50 data points that describe morphology of materials and around 70 data points on surface activity. And we start with finding good descriptors for those materials. So we came up with a descriptor that combines, it's a hybrid descriptor that combines information about the raw material and also about how the raw material is converted into a product. So, for example, for raw material, we describe it as a surface area. We have some information about chemical composition of a clay, cation exchange capacity. Then after the raw clay is treated, we have information about the additive. So, for example, pKa for acid that was useful to treat material, molecular weight of acid, number of hydrogen donor acceptor for more complicated molecules, and so on. And then we have some properties, some descriptors describing the process of converting this raw clay into higher volume product, like what type of activation, the milling time, amount of additive use, and so on. And for those samples, treated samples, we have the properties, experimentally measured properties like surface area, and micropore content, and so on. So the idea here is to build a model that will combine those descriptors with the measured properties. And we will use, again, one of the decision tree-based algorithms, in this case, extra-trace regressor. So here is our results, our models for those different properties: surface area, external surface area, percentage of micropores, and so on. And the red points are basically test sets. So those are data points which were not used to build a model. Those are only data sets that were used for training. And as you can see, those models work pretty well. They are pretty accurate. And that means that we can use them now to explore the parameter space. So, for example, what we can do is we can perform virtual experiment and see how those properties changes if we change certain parameters in our models. So, for example, we can look at how those descriptors that describe how the clay is treated affect properties. For example, amount of acid used for acidic activation, or amount of humidity present in the clay. And we can do it in many dimensions, so basically all dimensions that the model contains. But here, for practical reasons, we just show the plot in 2 dimensions. We choose 2 parameters for which we see the largest changes in properties. But those are so far the basic properties of clays. We are interested in catalysts, so we think about how we can combine those simple properties, or how those simple properties can determine acidic activity. And we came up with this design function. So basically, one parameter that describes this activity in this decomposition of chlorophyll application. And this design function combines surface area, surface pH, and also we try to minimize micropore content for this material. So we build a design function that is a function of those 3 basic properties. And we can do, again, now use our machine learning model to investigate how changing different parameters that describe this process of obtaining a clay, and how we can maximize this design function. And here are a few plots. We choose only 2 parameters for which we see the biggest changes: the amount of acid use in acid activation and relative humidity. And from all the materials that we investigated, the family of materials that have the largest design function, so that the largest potential for this application, was Parogoskite. And with the best material, we marked this P1. And we went to a lab and made this this material. And here in the table you see comparison of measured properties with predicted properties, and you can see that our predictions were basically confirmed in experiments. So in final step, we took our best material and tested in this acidic degradation of chlorophyll, and we find out that this new material allows us to do almost 80% conversion of chlorophyll, and this is 2 times improvement over the raw material. So this is a demonstration basically how we can use machine learning to design new materials while at the same time limiting the number of experiments. And this concept can be repeated for different applications. I just illustrate you another application that we're interested in the area of nanoporous materials for food safety. So there's a big problem with food and animal feed caused by fungi. So fungi grows on crops, and you might have seen actually in the market a crop with fungi, and those fungi produce mycotoxins that can be very dangerous. So those mycotoxins enter, they're on a food or animal feed, and once they enter an animal, they can cause various health problems. This whole family of those mycotoxins, some of them are regulated, others are not yet regulated, but it's very important that animal feeds maintain the safe levels of those mycotoxins. So one of the ideas is to basically to mix adsorbing material with animal feed in such a way that those mycotoxins are adsorbed on the material in the gastral tract and removed from the animal body before they are adsorbed into a bloodstream. So we are interested in designing a material or a composition of materials that will capture those mycotoxins. So how can we do it? So here we focus on those nanoporous clays again, and the question is how we can what is the performance measure in this application? So if you think about it, if I said the idea for this application is mixing this material with animal feed, and the whole process will take place, adsorption process and removal through the gastral tract. So there are 2 stages. It's basically adsorption in the gut. So where the first this toxin is going from the food in the gastral tract and absorbing the material. And then what is really important, as a material with this adsorbed toxin moves through the gastral tract and then is removed through feces, we also want to know how much in this process, how much of the toxin is left in the body, how much is removed. So we have another parameter called the efficiency that measures basically corrects for the amount of toxin that was desorbed during the gastral tract. And we can measure those properties, this adsorption and efficiency, through in vitro experiments, and we rely here on a commercial test provided by Trilogy Analytical Labs. They basically this experiment that takes a few hours that imitates gastral tract. So there is a 3-hour stage with a low pH, and there is a 3-hour stage with a high pH to measure adsorption and efficiency of adsorption. And we can also do in vivo trials using live animals, but we try to limit those in the spirit of this 3R principle that aims to replace, reduce, and refine experiments, so we cause little harm to animals. So to summarize, this is the pipeline we are thinking about to test. We want to build a model that will work with different mycotoxins. So we want to include mycotoxin descriptors, molecular descriptors. We will have some material descriptors, like the one I mentioned earlier that describes nanoporous clays, and we have in vitro experiments that measure performance of those materials in this application. We want to build random forest models that predict efficiency and adsorption for those materials, and use those models to screen different compositions of a composite material based on various nanoclays. And for final candidates, we will do testing. So here it's information around model. In this case, we have about 85 data points. some were natural clays. We also have some composite materials based on two clays. And in this case, our descriptors for the mycotoxin, we use the descriptors that are often used when dealing with organic molecules. So molecular weight, number of hydrogen bond donors, acceptors, and some surface area, and some other physical chemical descriptors that are correlated with or correlating with adsorption of organic molecules. We have descriptors of clays, as I mentioned before, and also some descriptors of the process that tells, for example, how big the dosage of toxin and this clay was given. So what's the ratio between those two? And giving this the structure of the model, we can build quite reliable models. So you see the R-score are quite high for both predicting adsorption and efficiency of removal. So here the red points are the test set, which is basically the data points that were not used to build a model. You see they are almost on diagonal. So we have very good predictions. We also tested this model, how it works for different toxin molecules. So here are 3 examples of different toxins with different chemistries. And as you can see, the points, basically our predicted efficiency confirms the experimental efficiency. So we can demonstrate that our model works for different molecules. And we can analyze those models to see what are the important factors for coming from the mycotoxin, from a material and the condition where it's adsorbed. And we see, for example, from the conditions that important factor is how much of this detoxifying materials we include in the experiment. From material features, we see that clays that have high magnesium content tend to work better. And in case of features important for mycotoxin, this is quite a mixture of features that are important, but water solubility seems to be important. What is also interesting that now having our model, we can screen different compositions and identify the best mixtures of clays. And here is an example where we have we look at efficiency of adsorbing of the Zen toxin, and the linear plot is basically what would be the adsorption if we mix 2 clays and assume they don't interact. And the red is what our model predicts, and the difference is basically a synergy that is a result of building a composite materials of 2 different clays. And as you can see that our prediction is there is also experimental data point, and you can see that our model can predict the synergy, maybe not the volume exactly, but the trend is there, and we can do it for a number of different compositions. And again, you can see we can see that our models can predict this negative and positive synergy, and you can see that experiments confirm our predictions. So now having those models, we can really tune or look for what is the composition that gives the maximum synergy and a large efficiency in removing those mycotoxins. In practical application, we can even improve this adsorption by mixing this composite material based on 2 clays with additional amount of activated carbon. So we can also build a model that has the amount of this activated carbon in this nanocomposite materials, and we can also find the 2% of activated carbon is improving efficiency of removal of those toxins. So the final composition that we identify is actually commercialized by Tulsa and can be bought by or found under the name of Atox and HS Silver. Here is another example that now using our model, we can screen through virus toxins, and this is important because, as I mentioned, there are some toxins that are not yet regulated, but they will be regulated soon. And with our approach, we can already start designing composition that will work towards those other toxins. So we can basically think about this design process, what will be needed in a few years, and we can already include it in our products. And finally, there's a results of the validation of the best composition that we identified. We have this in vivo experiments that involved eight chickens, and 4 of them were given this nanoclay composite and a toxin, and 4 of them were given just the nanocomposite, and we were monitoring the amount of toxin in the bloodstream from the moment of admission. And you can see here on the plots that the one with our material have much lower concentration of toxin, just confirming the good design. So here I will be finishing this presentation. I can say that this formula of building this digital twin model of real experiments and applying to different models can be used in various different applications. And we have some ongoing work that, for example, focused on a nanoclay polymer composite to be used as a drilling fluid application for geoengineering applications. We have ongoing projects looking at fire safety properties for polymer with inorganic and organic additives like MOFs to improve fire safety. And we can build descriptors that hold information about this nanocomposite and correlate it with properties that are important for fire safety, such as peak heat release rate or time to ignition. And here's just a few plots of this experiment versus prediction. And as you can see, in those applications, we can build very good models, and we can use them to design better materials with least amount of experiments. So I will finish here. Just to summarize, I think I showed you a couple of examples how we can use statistical machine learning to build structure property models that can later be used in materials design. I stress the importance of descriptors, especially when you work with random forests. And I illustrate you a couple of examples why we have to think about what is important, what features are important, and descriptors should capture information about those important features. And that's it. So thank you very much for your attention.
Thank you very much, Maciej. So there are no questions yet. I think the amount of working applications is outstanding, and I love the versatility of these techniques and how you have gone to tune the composition of materials to then introduce also processing conditions, now synergistic effects. I think it's very interesting, and I don't know if you have any idea of which other fields you will be able to tackle in an upcoming future with these techniques.
So there are two areas that we'll be looking through the new projects that are coming. As one application is in porous metals. So right now there is a tendency, this additive manufacturing and 3D printing, we can print porous metal structures. And what is very interesting is if we can use this kind of experience and our descriptors that we developed for a really nanoscale for MOFs and zeolites, but those descriptors describe shapes, describe topology. So in principle, they can be used for larger scale objects like porous structures that have micro or nanometer scale pores. So one project we'll be trying to build those models predicting mechanical properties of porous structures using similar frameworks. And another interesting application, I think when I was talking about the simulated models that were based on simulated data, that there's not much to be done. and this is my personal opinion, that we've done everything. The real bottleneck is right now how we synthesize materials. It's very difficult to synthesize new MOFs that were previously designed by a computer. And one of the avenues that is possible is look at composite materials. So if we move to MOF, polymer, composite, for example, for those materials, we can run simulations that can be fairly easy, make an experiment. So there is a opportunity to design a new composite using those techniques and then immediately verify using experiments. So those are two directions I'm thinking to go into.
That's great. So we have one question. Kemal Bartu asks, is it enough to check the accuracy of constructed model according only to R2, in which case the phenomenon gets more complex? I don't know if you have access to.
I think it's more complicated. So R square is just one metric. So you should look at the mean absolute error or mean square error, because it's also important metric. I usually like the first assessment to just do visualize, just look at predicted and simulated, because it gives you very fast the idea where is the error coming from. If it's just few data points that are off by a lot, or it's like general tendency of the points are far away from this diagonal. For classification kind of application of machine learning classification, there are other tests like area under the curves that can be used. So there are different options, and using just one metric is not enough. You need to look at a couple of metrics.
Okay, so there are no more questions. Oh yeah, here. Let me check. Okay, so regarding the application of the surrogate model, there was a part about exploring the space. Which techniques has been tried to explore the space? You can read it in the chat if you want.
So surrogate. So once we build a surrogate model for, I guess, experimental data, those models are still fairly simple. So what we could do is use them in brute force. So basically, we enumerated a large database of possible candidates just by looking at the range of possible descriptors. So we can basically generate a big array that holds those prototype materials, and for each material in this array, we could use our machine learning model to predict properties. So it was basically a brute force exploration. Although other techniques are possible, you can use genetic algorithms, for example, to do it if the model is not efficient. But in our case, those models are fairly small, and by using modern computer, you can do this brute force search. Okay.
Great. So I don't know if there's going to be any more questions from the audience. Yeah, we have one more. Could you explain in more detail again what you're comparing with the in vivo validation for the detoxifiers?
Can you read the question? Or the comparing?
Yeah. Could you explain in more detail again what you're comparing with the in vivo validation for the detoxifiers?
In vivo validation. So we have in this case we work with chicken. So we can take a blood sample and measure amount of toxin in blood. We can also So one test, so this is the plot on the left, is basically amount of toxin over the time since the toxin was administered. And the second is another test using a biomarker. So this is there's a biomarker which basically indicates the composition of DON toxin in the liver, and you can also look at concentration of this biomarker. And this is the plot on the right.
Okay.
Yeah, I will direct you this publication because I have to say this is the first time in my career where I was part of a project with live animals. So there's lots of those tests are new. So this project was just accepted in scientific reports. So you can find the publication with all the details.
Okay. Thanks, Maciej. So I guess there are no more questions. If something else comes up, you have Maciej's email in our website. It's very easy to find. So feel free to throw him an email. And with this, we put an end to this webinar. So thank you very much, Maciej, for the talk, and all the attendees.
Thank you for your invitation, and thank you everyone for coming.
Okay, have a good day.
Bye bye.
Bye.